Now that we're talking about phase changes, we finally get to introduce dynamic equilibrium, which is the theme of Chemistry 162. We will talk about this in terms of phase changes, and then we'll talk about it in terms of chemical reactions as well, and spend a lot of time on it. So, get to know dynamic equilibrium. So, for phase changes, what's really happening at dynamic equilibrium is when we see that rate of condensation, so gas to liquid, equal the rate of vaporization. So going from a liquid to a gas. This is going to happen. We'll reach dynamic equilibrium for vaporization and condensation if we have a closed system. So I like to think about it as I have a system and I pour the liquid in, like there's nothing else in the air. Like I have a vacuum, somehow liquid magically appears and I cap it to visualize this. And so that's looking really at this first one right here. What happens when I have nothing in the headspace above that liquid is I will have a high rate of vaporization. There's no particles at all in the headspace, so there's no condensation that can take place. So I'll have this rate of vaporization that starts occurring. And it'll keep doing the same rate of vaporization for this whole process. It'll be constant. And as then particles form, now looking at the second flask here in the vapor phase, now I have some that are in the gas phase over my liquid. Now they will have the opportunity to collide with the surface of the liquid. And if they're at a low kinetic energy, they can get captured by the liquid and form intermolecular attractions with the molecules there and become part of the liquid and condense. So once we have some of those in the rate of condensation will start to increase as we have particles in the headspace above the liquid. And as more and more and more particles are in the gas phase, as that rate of evaporation continues to produce gas phase particles, then we'll have more and more particles that might have a low enough kinetic energy to rejoin the liquid phase. And so what we do is we see the rate of condensation start at 0 and then increase until it hits the same rate as evaporation. And then at that point, what's happening is the particles are evaporating just as fast as they're condensing. And then I would stop, I would, through this process, be seeing a change in pressure, right? It would start at 0 and it would increase and increase and increase. And then the pressure would stay the same. And that would be the vapor pressure of the liquid. Um, and it's going to be higher the more volatile that liquid is, because more of our particles would be easier for them to evaporate to break those intermolecular forces. And so we'll see a higher vapor pressure at dynamic equilibrium for something that's more volatile than something that has stronger intermolecular forces. So let's think about things that can happen. So let's say you reach dynamic equilibrium, right? So you have the same rate of vaporization and condensation. What happens when we make changes to it? Um, and so when you have something at equilibrium and you make a change to the system, it's no longer at equilibrium, right? So in the case of a gas like this, we might increase the volume, which would decrease the pressure, right? Or we could decrease the volume. That's one thing we could do. We could increase or decrease temperature. That would shift this out of equilibrium. And then any system is then going to try to reestablish that equilibrium, because our rate of vaporization will still be occurring and our condensation will increase or decrease until they're the same. So let's take our initial system at equilibrium and let's increase the volume. And that's what this picture is trying to show right here, is an increase in volume. And when we do that, we have lower pressure for our gas particles. And so we're going to see, with that lower pressure of gas particles, less condensation take place, because the particles are going to take more time to travel around and collide down with the surface. And only a certain percentage of those collisions with the surface of the liquid are going to actually result in it becoming the liquid. And so the rate of vaporization is the same. We still have the same liquid in the same space and it's just evaporating. But as that pressure decreased, as the volume increased, the rate of condensation decreased. And it'll happen until the particle concentration in the gas phase increases. And so that'll keep happening. And the rate of condensation will increase and increase and increase as it fills with more gas until those rates are the same and they're back at dynamic equilibrium. And so what we'll see is that we'll be at equilibrium with a vapor pressure. We'll increase the volume and you might see a slight pressure drop, but then that pressure will increase until it's at the exact same vapor pressure again. So I can make these changes and the system will react and respond by modifying the rate of condensation. It's not like an intentional thing. It's just there's less particles to condense until they reach that equilibrium vapor pressure again. And so that'll keep happening. And so the really important takeaway here is that when you change the conditions of something that a system that's at equilibrium, it's going to shift the process to relieve the effects of that change. It's going to find a way back to equilibrium every single time, which is so interesting. And then we'll see this with chemical reactions and we see these with physical processes too. So let's look at the opposite now. So maybe even pause, think about this for a minute yourself and kind of formulate your idea. And then let's talk about it together. So explain how equilibrium will reestablish itself when the volume of the container is decreased. So here we're looking at the volume decreasing this time. All right. So as this volume decreases, right? Pressure increases. This is my change to equilibrium. So now I'm not in equilibrium anymore. So to reestablish it, my rate of vaporization is going to stay the same because nothing has happened to my liquid. But my rate of condensation is going to increase. So more particles are going to go from the gas phase to the liquid phase until there's less particles in that space, that reduced volume. And the rate of condensation will get smaller and smaller and smaller until it's the same. And that's when we've reestablished equilibrium. So if I decrease that volume, I will see my volume of liquid increase a little bit if I have the ability to see those subtle changes, because more of the gas phase will condense down into the liquid phase. If I were to expand the volume, then I would see the volume of the liquid decrease a little as more of those particles went into the gas phase to reestablish that dynamic equilibrium with the vapor pressure.